Okay, so good afternoon, everyone. My name is Eziama Ubachukwu, and Frank already mentioned, I'm taking this presentation on behalf of Andre Sonu, who is unavoidably absent, but I think we should be able to also get him on somehow digitally if there are questions that only him can answer. But then I'll just try my best to talk through the things he was supposed to present. So generally, I'm talking about the Living Lab Energy Campus, which is actually a project that's running in Forschungszentrum Jülich, somewhere in the western part of Germany. So the Living Lab Energy Campus is a test bed for future district energy systems. So I'll just try to run through this. Of course, the idea is that apart from introducing these user stories and success stories and techniques, is also for some points of collaboration. If there's something that particularly appeals to you that you'd want to talk about more after, then we're also very open for this. Now, so I'll just go through the introduction. Now, why are real-world test beds needed at all, right? So we know from research that there usually is a lot of studies on theoretical analysis of different scenarios. But then, like also Frank mentioned in his introductory talk, many times the real-world applications are missing. So what we try to do at Forschungszentrum is to bridge this gap and try to get the theoretical studies also into practice and to provide a framework that facilitates this kind of thing. And that's basically what I'm going to talk about for the rest of the presentation. Now, Forschungszentrum Jülich is a research center, pretty large for a research center that combines energy information, bioeconomy, and so within these fields. Some basic data founded in 1956 with 11 institutes and 80 sub-institutes, more institute divisions, over 7,000 employees and guest scientists, almost 1,000, and 166 buildings over an area of 1.7 square kilometers. So this is how it looks aerially. Now, in the Living Lab Energy Campus project, we have a setup of hardware, and basically we have this as the campus map, which we just saw, the Google version of it. So we have PV installations on campus. We have lithium-ion battery storages that also we study them together with bidirectional charging of electric vehicles. There is the combined heat and power plant that then has also hydrogen production as part of it to support the whole so this whole hydrogen as a storage or energy transport medium idea. Then so also LOHC, liquid oxide hydrogen carrier. And then we have electrolysis machines, a climate neutral office building that is under construction. So Q1 of 2025, that should then be inhabited. And then finally, we also have waste heat from a high performance computing cluster. So Jülich houses one of the big supercomputing centers in Germany. And from there, we have a lot of waste heat. Then we then have these buildings that we are making smart, so cognitive buildings. And then the next slide, I'm going to talk about these two buildings, basically. Now, we have all over the campus buildings where we've installed sensors and actuators, basically turned into smart buildings. Some of them we're able to control. Some of them we only can read data from them. The 16.17 building is the one that I also showed that is a climate neutral building, that it's under construction currently. And actually that's where our office is going to be after it finishes. So we'll see some more details about this later. But then at the building level, we have access to meter data, which is used for billing at the research center. And then also through the BACnet protocol, these components are integrated together at the floor and wing level. We have also additional meters for heat and power. At the loom level, we have these wireless sensors, smart thermostatic heater valves. So the wireless sensors measure like CO2 concentrations and temperatures in the room and humidity and so on. And then smart heater valves also. So basically, we're trying to replace all the whole old heating and to something we can control digitally. And also some buildings or rooms have additional sensors for occupancy and so on. Now, this is just like an architectural top view of what the protocols, communication protocols on the hardware layer look like. So there's KNX, there's a CAN bus, there's BACnet. So these are for people who are also specialized in these areas. So I'm just presenting them in case there's a part of it that you're interested in. But then the devices all communicate with different protocols, and we try to merge all of these things together and then have a central ICT platform where all the data is stored in and where we can also retrieve it and do all of the analysis we want to do and all of the control of the buildings. Then now I'll talk about the LCT platform where all of this data flows to. Basically, there's the applications layer, which runs in the cloud, and a lot of applications can run there that deal with monitoring, forecasting, optimal control, simulation, optimal design. So all of these, we have applications in this layer. Then we have the middleware, of course, that connects, the real world, the field, and the sensors with these applications. And basically, in the next slide now, we're going to see what the inside of these first two layers look like. Weather forecast, room occupancy, forecast from meetings schedules. Then we do data analysis. There's model predictive control and state estimation for where we don't have all the data. There's dashboards, visualization, which is one of the main places that I also focused on during my PhD. Then in this middle layer, we have the storage layer and then the data transmission layer. And then, of course, libraries that also help us to do modeling. And these then are connected to the hardware part, sensors. Okay, normally this doesn't show on screens. So sensors and actuators that actually receive commands from the controllers and implement them in the real world. So that's the basic layout for the ICT platform. Then the idea now is that it is possible to replace some of these components that we developed with external components for testing. So this is almost like infrastructure as a service, more or less. So controller algorithms, new model predictive control, so from external parties, then can be integrated into the system. So this is also where we're interested in collaborations, for example. So any of these virtual demonstrators, weather forecasts. Now, to allow this, we have a system in place to make sure so that there is some security, because this is an experimental framework, but at the same time, these are real users. This is a real world environment. So the name Living Lab Energy Campus is actually real people, real buildings, real. So there's no distinction in that sense between what you're running experimentally and what you're using in the real world. And of course, the users themselves and how they perceive your solutions is also something that we can consider in this case. So normally the default operation is that all these controllers have their own default way of working that they're pre-programmed to do. For example, the heating can actually run by itself. It's a smart heater, right, valve. So without external instructions, it can already heat the room. It's pre-programmed to do that. So, but then we have all of these experimental things now in a cloud layer which replace or give instructions to the local controller. If anything goes wrong with the cloud layer, there's the opportunity to switch back to the default mode. So we have what we call a kill switch that was part of the design of the system, so that if anything goes wrong experimentally, we have a fallback plan, so that at least the security of supply, for example, and security of basically lives is guaranteed. So let's look at some exemplary use cases, and that's where the last part of this presentation. Now, some of these are full PhD projects, right? So I don't expect, even these are not my PhD projects. So even I would not know all the nitty-gritty details. So I would also not expect that everything here will be understandable at once. But I'll just try to summarize what these talk about. So we have an optimization framework that's called Commando, developed by one of our colleagues, where we model these energy systems, now no longer by writing directly the mathematical formulations and the rest of them, but actually modeling the system components separately as, in an object-oriented manner, and then being able to then use the framework to connect these systems. So all the flow energy balances, for example, that are required can then be modeled directly using these objects instead of writing mathematical formulations. Then this can then be translated into the actual modeling formulations that can then be solved by, for example, Gurobi and some other solvers also. So this is kind of, we designed it to be open source and then to be generic enough to be used for different solvers. Then we have an example of the use of that, of this framework. So for example, you can see this representation here is very similar to what is here. So one of the things that I presented in one of the former slides is that we have these supercomputers and then the waste heat coming from them. So one of the PhD projects that finished about 2 years ago was to design a piping network and basically an alternative energy system that uses the low temperature waste heat supplied from the supercomputing. Normally, this heat is just thrown away. This waste heat is thrown away, or the wastewater. It's too low for the normal district heating, so 40 degrees-ish, while district heating could be 80, 100 degrees. So, but then instead of throwing it away, we decided that we could actually use them to power the heating for the buildings. And one of the innovative things about it is that normally in such an analysis, people usually assume a constant waste heat, so supply and then a constant return temperature. But here, using this framework as the modeling platform, some more detailed, quite detailed, complex mixed integer, non-linear actually, and quadratic constraints had to be solved. And that was also done with Gurobi to be able to do this. So, and it was better with this varying supply temperature, which mimics more of what the real world is, to actually get more performance from the waste heat than what is normally assumed. Then we have another colleague who worked on a framework he calls LinMog, which is basically moving from data-driven modeling to linear or piecewise linear formulations. So, and it's been applied in a real-world case. Starting from the top here, we have basically some real system that generates data. That real system could actually be some function or some mock-up model, simulation model. And then it goes into this framework, and then this framework then produces a simplified linear optimization model that can now be used for optimization, which is normally faster to solve. Here we see what the flow looks like. Then on the other side, there was a project at the research center that ended in the late 90s, where there was an electrolysis experiment that was on. So there was a lot of data. And then within this, you can see the operational data of the electrolyzer there. On the left side, on your right side, but on the left side of the right side. And then the piecewise linear model of it that is produced automatically by this LinMock framework. And then also we can see that this is configurable, how many points you want to use for the linearization. So that's also something that data also that was tested and within the LLEC project. Then we have this new building I talked about as a climate neutral building. It was already, the energy performance of it and or the climate neutrality was already, simulated and studied by another person as his PhD project. So based on this, the building is now being constructed. So basically, there's this very tight connection between what we produce in terms of research and what is done in the real world, the temperature heating network and this building. And then what we have here is that we have these models developed with XLib. It's a modeling library that's also for buildings especially. And then from that, a hierarchical distributed model predictive control is run on it. And then the results are produced. They've been tested in an actual building that we use for experiments, a real building where real people sit. And then because the original building that it's intended for is not yet completed. So there's always this relationship between what we produce in terms of the theory and then being able to test it out with the things we have available. So the last slide, we have some projects that are now leveraging this infrastructure. This one, so these are pretty new projects. So there's Interstore, and here test of protocol adapters where for all of this hardware communication and real world demonstration of coupling of different energy domains. And then we have the funds SNM, which actually tries to do state estimation. So hardware sensors, how accurate can we get if we replace them with software sensors that use other kinds of data to represent what's missing. And then test of third-party scheduling and algorithm also for the low temperature district heating network. So these are example projects, and we also look forward to having more projects like this. If people also have ideas about these kinds of things, then it's easy to get funding for them. So basically, that's the end of it. Thank you very much.
So Eziama, basically the message to the audience is also you can
switch back.
You can be contacted. You offer to be contacted by software vendors, by
hardware vendors,
consumers, hardware vendors to actually make use of this testbed.
Yep.
And you offer this collaboration. So maybe this is something you want to discuss with the team. So we have a couple of minutes left where you will introduce the PowerGame, right?
Okay. Yeah.
So there's not much time to play it because we are all busy here the 2 days. But you will explain how to get to that game, how to run it, and then we'll see what we make out of that the rest of the summit, and also in a separate webinar which we then offer. Thank you.
Yeah, thank you. Yeah, I can already introduce myself. My name is Riebesel. I'm also working at IK10 of Forschungszentrum Jülich. I'm a scientific software developer, and I'm part of the core development team, I could say, of the PowerGame, together with Eziama. I'll hand over to Eziama now.
Okay, so yeah, this was actually my original presentation. So I'll start again. So this presentation I share with Leah. So I'll just introduce, and then Leah will talk more details about the optimization part and some other technical details about the game. So the PowerGame is just an educational game that was developed at Forschungszentrum. It was also part of my PhD work. Now, it's what is called a serious game. So a serious game is not a game where you play seriously. but it's a game where the purpose of the game is beyond mere entertainment. Flight simulators, for example, are serious games. You could enjoy playing them. They look like games, but the real reason is to train pilots. So something like this. That's a serious game. So in this game, the idea is to design an alternative energy system for the Forschungszentrum Jülich campus, right? That minimizes CO2 emissions. So actually, all the current energy systems are taken away in the game, and then you just build something afresh. And a set of energy system components is provided, and then a budget within which to, for example, 10 million euros. This is just within the game, not real life, to design this energy system. Now, the overarching purpose is what is depending on the game mode. There is competition mode, in which case teams compete. So to design. So one team proposes, makes a design. Individuals make designs, and then they say, "Hey, team, I made this design." The game allows all of these things, and we're going to see that shortly. And then people vote on the designs. Okay, we think this is the best, and then that represents our team. And then after this, the simulation is run, and the teams are ranked based on how they were able to minimize CO2 emissions. Fun fact is that the game is actually available and running now. So if a couple of people have signed up and are playing, and then until the end of today, you can also do the same. Try out your hands, but Leah will also talk more about that. There's also the sandbox mode where there can be personal exploration, and then the real-time mode that is like a digital twin where we get data from real world. We talked about the buildings and that they are already monitors and they have sensors. So, but is the competition mode that is the most developed now. We are working on the other modes of it. Now, I'll talk a bit more about this competition mode. The first step is just design in teams. It's a drag and drop interface. So basically, you choose whichever component you want to install. This is the decision of the player. And then after the design and the designs for the teams are also chosen, Leah will talk about that. There's an optimization that's run. Leah would also go into a little more detail about the optimization, so don't worry about this. Then there's the simulation where the teams are then ranked based on their CO2 emissions. By tomorrow, we'll have a screen that shows this simulation for the game, for this for the Gurobi Live, basically. Then in Forschungszentrum, we had a context for the game. It wasn't just a game by itself. Here, we're playing it as a game just for entertainment and try out your hands on some of these things. But in Forschungszentrum, it was more than just a game because it was linked to the real world. How? We have real world users that interact with the windows and basically the heating system of the buildings that they sit in. And then we have a couple of systems that were developed. This was also part of my PhD that now try to estimate the energy efficiency of the behavior of these occupants, right? So what we're seeing here is traffic light red, so poor performance, too much energy wasted in the rooms. And then this energy scaled to the whole campus is transferred to the game as a penalty. Meaning that as you're acting in the real world, your buildings in the game are getting worse, depending on your behavior in the real world. So this is already what we've tried out. It was an experimental run that we ran for 8 weeks at the beginning of the year. And then what that means invariably is that your CO2 consumptions also get worse. Our CO2 emissions get worse in the game and your team performs worse. So there's that drive to make users or office occupants save more energy. That was the whole idea behind it. Yeah. So Leah, over to you for the energy system.
Yeah, thank you. I will now come to the part that actually involves optimization in our application. So We can see in the game already in the visual interface that we are looking at Forschungszentrum Jülich campus. What does the demand actually look like in the campus? We have a lot of laboratory and office buildings, and we are lucky enough to have measurement data for all the buildings individually. So we can base the demand in their game on actual historic data. So for each building, we can actually look at the electricity and also the heating demand. Now, how do we supply this demand? For this, I would like to look at the energy system architecture that we also provide in the game interface. Here you see again the buildings that represent the energy demand. And in blue, you can see the electrical network, and in red, the heating network that both supply all the buildings. And you can also see how the components connect to these grids. And the arrows indicate the possible directions of the energy flow. For example, for the electricity grid, we are able to import and export electricity. And some of the components are also connected to a gas supply grid. Now we assume in the game that we have a default energy supply system, which is always there. Even if you install new components, there's always backup. This is also necessary from an optimization perspective. That way we always have a feasible optimization problem. And this involves a connection to the public power grid and oil boilers that centrally supply the heating network. Now, but you want actually in the game to have minimal CO2 emissions in the operation. And that's why we enable, for example, installation of renewable conversion units like photovoltaic systems and wind turbines. We have alternative heating systems like combined heat and power units, gas boilers and heat pumps. But we also allow the installation of storages, that is battery storages and thermal storages. And now in the game, we actually want to show in the simulation what this operation would look like of the designed energy system. And we want to operate it in a CO2 minimal way. And since by just rule-based systems or approaches, for example, it's not straightforward to find the optimal operation with regard to CO2 emissions and also operational costs, we decided to use mathematical optimization. Now, to understand our optimization modeling approach, I would like to talk a bit about our specific software application constraints. So in the game, we have to calculate the operation of all the team's energy systems. So we have to run multiple problems, one per team. And the optimization run is actually performed during the game. So we have limited time to finish the optimizations because we don't want people to wait for their results for a very long time. But then the purpose of the game is to get a general idea about the energy supply in a more climate-friendly way. So we allow for a reasonable model complexity or model accuracy, but it doesn't have to be very high because we don't want to make real-life decisions based on this. So we actually went for a mixed integer linear program with an objective function that minimizes both the operational CO2 emissions and the operational costs. And these terms are weighted. And now let's look at the constraints. First of all, we have energy balances. So the demand has to be covered by the backup supply and also the newly installed energy components. And then we have, of course, technical constraints that are due to the dynamic operational behavior of the components that we install. Here we have, for example, specific storage constraints. This is the state of charge that is dependent on the state of charge of the previous time step and dependent on the energy that is charged or discharged. Then, for example, for the combined heat and power unit, we decided for a realistic approach of the operation, we need a minimum part load constraint. So there's a minimum power that has to be used from the CHP. Now, because we wanted to limit our model complexity to have it run in a reasonable time, we made some limits by, for example, leaving out ramping constraints, minimum operation time constraints, and part load efficiency constraints, even though they would have been relevant for sure in our model. The inputs that we need for the optimization are energy demands. Well, we consider this over 1 year, outside temperatures, and cost and CO2 parameters. What we get from this is the optimal dispatch or unit commitment for the energy supply components and the according energy flows. Based on this, also the operational CO2 emissions and operational costs. Now we want to look at where this optimization is actually embedded in our software application. This is a simplified version of our software architecture. It's actually separated in 2 parts. You can see the uPower main app and an optimization coordinator. This is because we wanted to dedicate certain computing power to just optimization, which can be run separately from the main app. And the 2 parts of the app can communicate over the protocol MQTT over network, which is displayed here. So the 2 parts can actually even be run on separate machines. One of the criteria we had to look at when developing this architecture was we wanted to have automatic handling of the optimization problems. That's why we have this component, a task factory that gets the input data and then automatically produces the optimization problem tasks. And we have the simulation coordinator, which tracks the time in the game. It keeps track of the different game phases and activates the optimizations and handles the optimization results. So this simulation coordinator can send data to the optimization coordinator. And this is then received by the optimization manager. And because we want to be able to cancel optimizations during their actual run, we let the optimization manager spawn sub-processes, also called optimization runners, to actually run the optimization. And now, because these different parts of the app can always crash, we also implemented a cooperative communication approach between the 2 parts of the app. So if one crashes, everything can still be built up again, and the process will be restarted from the right point. Now a little outlook. What are our extension plans? We want to move from the modeling language Pyomo to Gurobi Pi. We want to generalize the game to other settings, especially from the demand point of view, for example, with other campuses. We want to include hydrogen components like electrolyzer, fuel cell, and hydrogen storage. We want to enable design optimization so that we can have a benchmark we can compare the team's designs to. And we want to implement further modes. Eziama also already talked about this in the beginning. We want a real-time mode where we use real-time measurement data and have more detailed component models. Now, after this theory, we want to call to action with the ongoing competition, as we already mentioned. You can see the link to the game here. It's a browser-based app, so you're welcome to actually go there and sign up. The design phase is happening today until the end of the day. The results will be available tomorrow, and there will be even a few goodies for the winning team. Now, as the end, I would like to give a little live demo. Yeah, so this is the login page. Once you sign up for the game, you can see this. Okay, question, please. Yes, for sure. Good point. It's not really enabled for for mobile devices. Yeah, it's better to use your computer. So this is the login page. Okay, this is hard. There's the cursor. Nice. This is me. So when you log in, you first have to make sure you are registered for a game run, and then you are admitted to the right game run, which is called, I think, Gurobi Live Barcelona. Once you're registered for this game run, you can enter it like this. And this is the home page of the game. Here you can see the main actions that are to be done in this game. So it's design an energy system, then propose it to your teammates, and also vote for the designs that you like. You can simply click on this, and then you arrive at the design view. This is the well-known architecture widget. Now, let's choose, for example, a PV system. You can simply drag from here, drop it on the map, and it's there. You can still move it, drag it around, and you can resize it as you like. Let's make this a little bigger. And you can see the available cache changes. You can even remove the component with this. Okay. Oops. And this doesn't mean it just goes to the trash, but you're able to resell the component, so to speak. So you get the money back. So once you want to look at the current status of your energy system, you can click on this propose button. You have an overview of the peak demands of the system, your installed power, and a list of your installed components. And most importantly, probably, you have the yearly progress of the electricity and heating demand that you have to cover. Once you're happy with this design, you can propose it to your team like this. It's best to name it. And in this box, you have the opportunity to let your teammates know what your idea was when you designed this energy system. Okay, you can see all the proposals from your team on this page. So you get, again, the summary, and you get the opportunity to upvote this design. Now, maybe you don't have the time to discuss in person with your teammates. That's why we have this chat functionality. You can simply discuss here. And yeah, this is actually the end of it. That's all. It's simply as that. Thank you for your attention.
Thank you very much. It's break already. So, but a question, David?
No, it doesn't affect
doesn't
the production for PV, for example. Yeah, we decided not to include that. It was there in the plan, but for now, no.
Just wanted to ask, what was the driver behind your switch to Gurobi Pi, and what does it give you that Pyomo doesn't have?
We actually found that it's more efficient, so it's actually just faster in execution. And also, it gives us more handles on Gurobi itself. For example, for the process of canceling or aborting the optimization process, That's where a Gurobi Pi gives us functionality to do that directly in Python.
All right, we don't want to keep you from the break. So the offer to collaborate with Forschungszentrum is on the table. The offer to get advice on the game is also on the table. Tomorrow there will be a monitor in the exhibition space with live demo, right?
Yep.
Okay. So yeah, and very likely a couple of weeks after this event, we're going to set up something as a webinar, and where actually tons of people hopefully will participate in this game, can form competitive teams, and we will award something to the winner. Thank you very much.
Okay. Thank you.
And enjoy the break, and see you again in 20 minutes.